So now we'll talk about seeder particles or the tracer particles in depth. By now you should appreciate the importance of seeder particles, because to visualize the fluid, maybe water or gases, it is really important to choose appropriate seeder particles, because those are the things, basically the entities which are actually helping you visualize the flow. So actually it should faithfully follow that flow and not behave on its own, right? So yeah, I mean, these seeder particles are used to see, I mean, how the flow is evolving in time and space, right? And there are a lot of issues related to that, but yeah, again, it is one of the most important experimental decision you should take, because if you take a bit larger particle or a smaller particle size, it can actually alter your results significantly, and this should be taken care of before starting your experiments. Another thing is the quantity of particles play an important role, because at micro scale, when you are dealing with channel size of micron scales like 100 microns or 50 microns, the particles should not clog the channel, and if it starts clogging or if it starts to sticking to the channels, it can disrupt the flow, and as a result you can get a varying kind of pressure drops across the channels, and you can get erroneous results. Many a times you are not even aware of these things happening inside your channel, so you should be very careful while doing the experiments and choose very accurately the quantity of particles. Another thing is actually the most important thing, your seeder particle should respond immediately to any change that is happening inside the fluid motion. A lag would actually result in some erroneous output again, and because if you want to see a very small a phenomena that is occurring over a very small time scale, your particles should respond that fast so that you are able to capture that phenomena at that small time scale, right? So it is very important that a small response time, the particle should respond at a very small time scales, because normally in microfluidics the time scales are pretty small, right? We are seeing things which are occurring over a very small period of time. We'll see a bit more about it in the next slide, how to derive the particle instantaneous velocity. Another important thing is we are talking about smaller sizes, the particle size should be small and those things. But again, if you start going to a very smaller side of the spectrum, the Brownian motion starts to come up, and it can actually start causing some kind of uncertainties in your flow. So we should be very careful that the particle should not be very small and it should not be very large to get the desired output. And this is just one image where you can see these are the seeder particles I am talking about. These are fluorescent particles kept inside a fluidic channel, and these white particles are, some of them are shining very brightly, some of them are not, because of the volume illumination, which we will talk about in later slides. Yeah. Now let us derive an equation for the particle velocity inside a fluid. So here you can see a particle of diameter dp, and say you have at time is equal to 0 a fluid that is passing over it with a velocity of uf. We assume this uf to be constant for now. We want to see how long this particle takes from t is equal to 0, from a basically static position, to reach the fluid velocity, right? So let us consider this, the instantaneous velocity of particle, to be up. To model this, we will just use a simple Newton's second law, where you can model for the particle, you can say that the rate of change of momentum, that is mass into dup by dt, is equal to the drag force the particle is facing. This drag force is because of the motion of the particle relative to the fluid velocity, right? If it is moving at some speed and if the fluid is moving at some different speed, there will be a relative velocity between them, and because of that there is a relative drag. Now this drag force can be assumed to be the Stokes drag here, and we can write it as 3 into pi into mu of the fluid into particle diameter into the relative velocity term uf minus up. On further solving this, you see that you can write the mass term as rho p, the volume, the density of the particle, into this volume of the sphere, 4 by 3 pi r cube, multiplied by the del up by dt, which is equal to the Stokes drag. On further solving this, you get something like this, where the rate of change of velocity is given by this term. Now you integrate both the sides like this, and you get the log of the relative velocity term is equal to the negative of this term plus a integration constant. Now to find the constant, you need a boundary condition, and as we already talked, we have a boundary condition, that is at t equals to 0, the particle velocity was 0. Now when you use this equation in this, you get the value of constant as log of the fluid velocity ln uf. You plug this again back to this equation, and you get something like uf minus up by uf is equal to e to the power this term. Now if you actually see this term is basically nothing. If you write the units of this term, you get something like kg per ms, this is the dynamic viscosity, multiplied by, there is a rho term there, so that is nothing but kg per meter cube, and you have this diameter square, that is this, and if you actually cancel the terms, you get a time inverse term. So if you name this equation as 1, so now this term standing there, sitting here, basically is nothing but 1 by t, and we actually, this is the relaxation time which we are talking about. Now this term corresponds to a time scale known as the relaxation time, and we actually name it as tau. Now again, I have written this equation here, like you can see, and now on further solving this, you get a relation which looks like up, which is the instantaneous velocity, is equal to uf into 1 minus exponential to the power of minus t by tau. When you plot this, you get something like this. It's very easy to plot, and it's a routine activity. You can see that the velocity of the particle starts to increase and then stagnates at a point where it reaches the value of uf, that is the fluid velocity, and the time taken to do that is the tau. Now you can understand that the particle takes tau time basically to reach from its initial position to initial velocity, which is 0, to the fluid velocity, and this is the relaxation time. Now the time taken by a particle to reach the fluid velocity scales as this relaxation time, as we saw previously. Now you know what is this relaxation time. So how do you use it? How do you use this information to basically say that, okay, this size and this relaxation time of the particle is convenient for your flow? So for that, you define a non-dimensional number, that is the Stokes number or the particle Stokes number, and that is nothing but the ratio of the relaxation time of the particle to the time scale of your flow. So what is the time scale of your flow? Basically the fluid time scale. So for example, as I told earlier, that if you want to see something which is happening over a period of 1 second, you cannot take a particle whose response time is much more than that, right? You won't be able to capture that phenomena. So if you know the fluid time scale, if you know the approximate time scales, then you can choose a particle response time that is much more lower than your fluid time scale, right? And in general, if it is less than 0.1, then that is actually acceptable. So a few word of caution here. Basically, when we derived the previous equation, the exponential decay of the particle velocity, we actually assumed that the fluid acceleration is constant there, and the Stokes drag is applied. Now if that is not the situation, then the solution may no longer be a simple exponential decay, and this should be taken in consideration if your flow is having a large velocity, or maybe the particle size is much larger. But in general cases, if I generalize it, the derivation we have done is a very convenient one to basically measure the tendency of the particle to attain a equilibrium velocity and can be used easily. So now we will solve a simple mathematical problem to find the relaxation time of a polystyrene microsphere having the following properties. This exercise is just to give you an intuition of how things vary at these scales. So you are given that the particle density is 1000, which is very near to that of water. The particle diameter is around 800 nanometers, and the viscosity of the liquid, that is water, is 10 to the power minus 3 pascal second. Now we have the relaxation time as rho p into del p square by 18 mu. If you put the values of each of the terms, you will get 1000 into 800 into 10 to the minus 9 to the power 2. You have to keep in mind that you are doing everything in SI units, divided by 18 into 10 to the minus 3. This gives you around 10 to the power minus 8 seconds. Now you can see that this time is already in nanoseconds, right? So for this order of the particle diameter, that is say 200 to 1000 nanometer, the relaxation time remains in the order of 1 to 10 nanoseconds, which are much smaller than the time scale that are associated with micro scale flows. So normally the micro scale time scales will be much larger than this, and if you find the Stokes number, it will be much lesser than 1. So you can do an exercise on your own to see if you vary this dp, how this relaxation time actually changes, and you will see there is a dependence of square term. So if you decrease this dp, your tau should decrease, right? So taking smaller particles are favorable when you are doing experiments. Now again, a word of caution regarding the density difference between the particle and the fluid. Now it is very crucial to select the seeder particle that has a density which is very near to that of your working fluid, so that we can say that the particles are neutrally buoyant and it is not tending towards any kind of buoyant force, which might not be the force that you want in your flow field, right? So using the Stokes drag and the forces on the particle, you can actually derive a UG term, that is the velocity induced due to the gravitational forces on the seeder particles. And now our aim is to basically minimize this so that this becomes very small and it doesn't affect your flow. So to minimize this, if you minimize this difference, you can get a very low value of UG, and this should be your aim before starting the experiment. And another thing is higher density would definitely lead to sedimentation, which again was what we were talking about, and the relaxation time will also increase, so we don't want that to happen. And now again, previously we saw that tau is directly proportional to the square of the particle diameter, which implies that your particle, seeder particle, must be very small, right, the diameter. But again, if it is very small, then the Brownian motion can come into picture, and that's why we have to be very careful while selecting the diameter of the particle. And there can be other forces like the electrical charges. If there is a flow that has some kind of electrical charges in it, that can actually act on the particles, and it can make the seeder particle to deviate. There can be other things like if you are dealing with some kind of active fluid or things like that, those can actually play a role while your seeder particles are moving into the flow. So one has to be very careful in choosing these particles, the seeder particles, when you are not dealing with traditional flow fields. And another very important thing which we should be aware of, that even after taking care of all the parameters like the relaxation time, the particle diameter, the density difference, it is still an assumption that the local velocity of the fluid and particle are same, right? Because again, there will be some kind of relaxation time that the particle will have, although very small, but it will have, and there will be some error, but this assumption is still a good one to get the flow field to a certain reasonable accuracy. Now we'll talk a bit about the Brownian motion, which probably everyone is aware of, and it happens, it is basically the random motion of liquid molecules due to the thermal agitation, right? So I'll just give you a pictorial depiction of what I'm talking about. Suppose these blue particles are basically the particle diameter, and basically these are your Cedar particles, and you have these molecules around it which are very large in number. Now if your particle size starts to becoming that small that it starts reaching the order of these molecular particles, then the interaction of these molecules with your particles can become very significant, and that can actually cause some kind of uncertainty in your flow, and that can actually deviate your particles, and this can be an additional force that actually starts acting on your particle. So we should be very careful with that. Now why is it important here? Again, it is important that the Cedar particle must not be very small, that its interaction with the molecules induce large uncertainties, and so we can say that Brownian motion actually limits the minimum particle size of the Cedar particle, which we should consider while doing micro PIV. So now let us see how we can actually find the mean square displacement between particles which actually perform Brownian motion. So if you find the relation, it actually looks like this, where you have, this is the displacement S, and the mean square displacement is given as 2 into capital D into delta T, where this D is the diffusion coefficient, and that is given as the ratio of Kb into T. This is the Boltzmann constant. T is the temperature in Kelvin, and this is divided by 3 pi mu into the particle diameter, and this delta T is the time scale, basically the image, basically you can say the time between which you are actually capturing your images. So if we say that the Cedar particles are following the flow faithfully, it will have displacement given as delta x is equal to the velocity of the fluid into delta T, and this velocity is basically uf, which is in the x direction, and again in delta y you will have vf, which is in the y direction, into delta T. Now this should hold good when we have confirmed that the Cedar particle is following the flow faithfully. So then, if we talk about the relative error that is caused due to the Brownian motion in the flow field, we can write it as this epsilon b, just a second, this epsilon b, which is the relative error, can be given as this term, the Brownian displacement, basically the square root of the mean square displacement given by delta x, and I am just solving it in one direction. So this is the displacement, the normal displacement of the particle, and if you solve it you will get something like this, which is the normal formula we derived in the previous slide, which gives us a relation that is 1 over uf into square root of 2d by delta t. So from this relation we can assume that for a low relative error, that is for a lower velocity of epsilon b, we should have a low diffusivity of the particle, and if you have a low diffusivity, your particle should be higher in dp, like it should have a higher particle diameter, which is again not desirable, and otherwise we can have a larger delta t, which is again very subjective, because normally this delta t depends on your flow, and it is a very subjective thing, and this cannot be randomly just kept on be increased, or it cannot be decreased. So again there is a trade-off which one has to consider, in case if you want to keep this relative error very small. So that's what I have shown it here, that this capital D is inversely proportional to dp. So if you want to decrease this capital this D, the diffusion coefficient, you have to increase the dp, which is normally undesirable, but yeah, there is a range for that, and you can choose a selective basically that value of dp which is giving you relatively lower error. So this is what I mean. To sum up, to avoid Brownian motion effects, you should have high dp, the particle diameter, and to avoid larger relaxation time, your dp should be low. So it is again a trade-off, and this actually a person who is doing the experiment should calculate these stuffs very carefully and then select their particle diameter. Now we'll just solve a simple problem which will give a better intuition of the relative error that is caused because of the Brownian motion. So we have a problem which says that we need to find the time interval between two images, that is delta t, that must be considered to maintain a relative error epsilon b value of 5%, and the fluid velocity in x direction is given by 100 micrometer per second, and the particle diameter is 500 nanometer. So let us start solving this and let's see where we end up. So we need to find the delta t. So first we'll see what is the diffusion coefficient, which is given as the Boltzmann constant into temperature by 3 pi mu dp. And if you find if you put the values of the Boltzmann constant and the temperature in Kelvin, you end up getting a value that is 8.7 into 10 to the power minus 13 meter square per second. This is the diffusion coefficient. Then the error term, that is the epsilon b, which we found out was to be like this. It comes out from this, what you have is you have the error that you want, that is 5%. You put it here and you get the delta t to be 70 ms milliseconds. And so basically this is the time which you should actually select if you want your error to be within 5%, the error because of the Brownian motion, and if you have these fluid velocity and particle diameter scales. However, I mean, this relative error can again be reduced, and it should be reduced because this what we are doing, the whole exercise is for a single particle. In normal conditions you have multiple particles, and so if you have several particles, it will intuitively the relative error will be reduced. And if you do some ensemble averaging over several realizations, I mean if you take multiple runs of that situation, you will you can reduce the error by a huge margin. So I'll just show you how we can do that. Now suppose you have three images, this is 1, this is 2, and this is 3, and you have in each images you have 4 particles. So basically this m is the number of images and n is the number of particles. So these are if you multiply these two, you get a term that is n. Okay. So the diffusive uncertainty decreases as 1 by root over n, right. So if you have a higher m, basically you have a higher root n, right. If you have a higher root n, the diffusive uncertainty actually decreases more. So basically if you have a larger number of images or realizations, you can have a lower error, right. So if the number of changes, if number of images m is equal to 6 say, and the number of particles shown here is 4, then the uncertainty reduces to epsilon b by root n, that is nothing but your epsilon n for single particle, epsilon b for single particle was 0.05 divided by root over 6 into 4, that is 24. This gives you the relative error around 1%. So see, I mean if you do a lot of experiments, you can get a lot of images and you can actually reduce the uncertainty error. However, again, doing a lot of experiments and doing ensemble averaging over larger realizations becomes very challenging over time. And yeah, so this is how basically you can deal with the relative error that arises because of the Brownian motion.